All right, so imagine a system, right? A system built for one of the biggest online stores on the planet, with one simple, kind of wild goal: to never, ever, ever go down. That's what we're talking about today. We're going to dive deep into the paper that introduced Dynamo, Amazon's legendary engine that was literally built to never sleep. I mean, really think about that for a second. What if your shopping cart, the one you're frantically filling up during Prime Day, could absolutely, positively never fail? It doesn't matter if a server blows up or a whole data center goes dark, your stuff is safe. That's the exact problem Amazon set out to solve. And here's why that is such an incredibly hard problem to solve. When you load a page on Amazon, it's not just one thing talking to one server. No way. That single click can trigger over 150 different services in the background. At Amazon's scale, with tens of thousands of servers, something is always breaking. Failure isn't the exception. It's just the normal, everyday state of operation. And this massive scale brings us to what was, no exaggeration, Amazon's billion-dollar problem. The paper puts it pretty bluntly. Even the tiniest little outage costs an absolute fortune. But more than that, it damages something you can't buy back: customer trust. See, when you're this big, reliability isn't just a nice-to-have feature. It's the entire foundation of your business. So the goal they set was both simple and totally audacious: create an always-on experience. Things like the shopping cart, the session data, they had to be available for you to write to and read from all the time. No excuses, no downtime, period. Now, to get there, they had to make a really radical choice. You see, traditional databases are all about consistency. They'll actually reject your request, you're right, if they can't make sure every copy of the data is perfectly in sync. Dynamo just flips that whole idea on its head. It prioritizes availability above all else, and that means it never rejects a write, even if it causes data to be temporarily out of sync. This obsession with availability leads to the core philosophy that makes Dynamo so revolutionary. It's this whole idea of being always writable. So you might be asking, how on earth can you never reject a write? Well, you do it by embracing this concept called eventual consistency. It's basically a promise. The system promises that eventually all the copies of your data will match up. It might not be at the exact same microsecond, but the system is designed to just keep working and sort all the details out later. Okay, so here's how it plays out in the real world. First, your write is never rejected. It's always accepted. Now, this means the system might for a short time hold conflicting versions of the same data. Imagine two different versions of your shopping cart existing at once. Then, and this is the absolute key, the mess gets sorted out when you read the data, not when you write it. The application itself, like the shopping cart code, has the smarts to look at the two versions and say, okay, let's just merge these into one. So, how did the engineers actually build this thing? I mean, what's under the hood? Let's take a look at Dynamo's technical blueprints. You know, the magic of Dynamo isn't really one single brand new invention. It's actually a brilliant combination of a bunch of well-known techniques. It uses consistent hashing to spread data out, something called a sloppy quorum to stay online even when servers are down, vector clocks to keep track of data history, and a gossip protocol so the servers can all chat with each other to stay up to date. Let's just zoom in on one of those for a second: vector clocks. The best way to think about this is like a family tree for your data. Seriously. It tracks the entire history of every single change, which lets the system figure out which version came from which, and most importantly, when two different versions have split off and created a conflict. Okay, let's walk through this picture to make it real. You start with some data, D1. A client updates it, and now you have D2. But then, two different clients update D2 at roughly the same time. This creates two conflicting branches, D3 and D4. Neither one of them is wrong, they just both happened. So later, when something tries to read this data, the system hands it both D3 and D4, and the application's logic is what merges them into a single, new, reconciled version, D5. So that's all the theory. But what happens when you unleash this thing into the chaos of Amazon's production environment? Well, let's look at some of the lessons they learned from the trenches. This is so important. Most places look at average performance. Amazon doesn't care about averages. They obsess over the 99.9th percentile. And why? Because averages hide the outliers, and those outliers are real customers having a really bad time. They literally build their systems so that the person having the slowest experience is still having a good one.
And this graph right here shows you exactly why that matters. Just look at the difference. The average latency is way down here. Everything looks great. But that 99.9th percentile is an order of magnitude higher. That spiky, unpredictable performance at the very edge, that's where the real engineering fight is.
And check this out. This is a fantastic example of how they tackled that tail latency. At first, they had a server coordinating all the read requests, but they realized that by moving that logic into a client-side library, they could get rid of an entire network hop. And look at the result. The 99.9th percentile latency for reads was more than cut in half. That is a huge win.
The system also had to adapt to the real world of operations. The way they divided up the data among all the servers, the partitioning strategy, it actually went through a few different versions as they learned what worked and what didn't.
So their original strategy, it was pretty clever, but it turned out to be really slow and complicated when they had to do things like add new servers or archival data. So they moved to what they call Strategy 3, which was a clear win across the board. It was faster, it balanced the load better, and it made operations way simpler, a massive quality of life improvement for the engineers. So after all this talk about conflicts and vector clocks and merging versions, you'd probably think the system is just pure chaos, right? Well, here's the kicker. In a typical 24-hour period, over 99.9% of all requests only ever saw a single consistent version of the data. The very conflicts the system was so carefully designed to handle, they're actually incredibly rare in practice.
So let's pull all this together. What is the lasting impact of this work? Well, that brings us to why Dynamo basically changed everything.
The legacy of Dynamo is just immense. It proved that eventual consistency wasn't just some academic idea. It could actually power one of the most demanding applications on the entire planet. It popularized this always writable model. And, crucially, it gave developers direct levers to pull to control the trade-offs between availability and consistency, and that paved the way for a whole new generation of databases that we all use today. Which really leaves us with one big question to chew on. In a world that expects every service to be always online 24/7, is the mathematical guarantee of perfect, instant consistency actually worth the price you have to pay, which is sometimes being offline? Dynamo's answer to that question completely changed the internet.